And I will post. Okay, so here we are. You learned about two methods of estimating returns. One was the idea of taking the relative change in market value plus the dividend yield, right? So we did capital gains yield plus dividend yield is the return at any given time on stock. Then I made an assumption about constant growth. And if you have constant growth, what you end up with is that formula turns into or converts to what is essentially the growing perpetuity formula. So we call that the dividend growth model. So those two models, the percentage return formula and then the dividend growth model with the assumption of the percentage return formula with constant growth, those two were the first two ways of calculating returns at any given time. The third way, and this is going to become the central focus of next week, is the capital asset pricing model. And we're going to lead up to that. So this is the first introduction. So our initial introduction. We want to make good value maximizing financial decisions. So we want to maximize the value of our stock, which in turn maximizes the value of the firm. And to do that, we care about in a stock issuing firm the relationship between risk and return. We like returns and we don't like risk. So we have to capture those with statistics that help us monitor performance, right, of our stock. And we talked about calculating the expected return as just an average and the variance or standard deviations of returns as a measure of spread or dispersion or volatility of that around the expected value, right? We also talked about having a portfolio that's diversified with several stock and that has a particular pattern over time. Historically, a well-diversified stock in the stock market, or sorry, well-diversified portfolio in the stock market, the returns to that portfolio are historically normally distributed. Okay, but for any individual stock, it's not necessarily true they're normally distributed, just for that kind of a diversified portfolio or the stock market in general. Okay. So back to this was the ex-ante data that I gave you for that quiz, right? Like 3 states of the world, probability and return. So this is just a review of that. If we get data like this, we can calculate the expected return and the standard deviation, and we will see, you guys could practice that. Here, the expected return will be 15%. The more likely state is the normal state of the economy. This lower, or you can call it a recession state of the economy, is state 1, and state 3 is the expansionary state of the economy. But the normal state, the status quo, is the most likely, and it has a mediocre, not mediocre, but an average type of return, or regular or normal type of return of 15%. But look at this one, 35% return, very nice. So putting all together, weighing the second one more likely, the average return is 15%. So you see here, this is right in the middle. This one is 30 points higher, and that one's 30 points lower. Do you agree? Is that 30? No, it's 50, it's 20 below. Okay, that's 20 and that's 35 above. But because this one has a stronger weight, it ends up being 15%. All right. So you guys could check that by adding it up. Now let's look at the standard deviation. In terms of the notation, remember, I don't care if you write the formulas like this or like just X and Y on your formula sheets, because you're not going to write formulas on your exam anyways. You're just going to use the formula. So whichever ones are easier for you to use, put those on your formula sheet, okay? So we're going to get the variance and then take the square root to get the standard deviation. When we calculate the variance of these returns, remember the bracket and the weight and the square and all of that, we get a standard deviation of 14. So the conclusion of this data, which you guys should verify if you haven't already, is that the expected return is 15%. And the standard deviation is 14. Now that's quite volatile, isn't it? Within one standard deviation, you're pretty much at zero return. So that's that's a risky security. So you're going to be close to no return. 68% chance of being between 1% or negative, 1% and like almost 30%. So it's quite spread out and volatile. So I'm going to introduce now, because investors don't just hold one stock. Okay, now, there are people who just buy one stock, like they buy Amazon or they just buy Tesla or they just buy, but it's recommended, and that's what financial economics was very focused on, is trying to find out like some general recommendation how to manage or how to invest in the stock market. And the general recommendation is that you invest in a well-diversified portfolio. And we're going to talk about what that means. So even though we've done the mathematics here, calculated the statistics for the distribution of returns and came up with this result, I'm going to give you two other assets, and we're going to calculate their expected return, their standard deviation, and then we're going to talk about their correlation. Okay, I'm going to introduce two. First of all, tell me about the relationship between these two assets. So they're both ex ante returns. I put them on a chart or a table with two assets. What is their relationship when you look at this data? What can you say about their relationship? How are they related? Nobody?
They
What do
have
you
an
see?
inverse relation.
Very good. Are you done? They're inversely related. When A does well, B does poorly. When A does poorly, B does well. So this is an example of negatively correlated returns or negatively correlated stocks. All right, so go through the trouble. Make sure you check this. Go through the trouble of calculating the expected return for stock A and the respective expected return for stock B, and they're pretty close to being the same. Now let's get their standard deviation. So when you get the standard deviation, first you get the variance and the standard deviation. So there are their standard deviations. Again, close. But we notice something. Let me put it all together here. And what do you notice? Whereas stock B has a higher, you could say comparable, but it's a little higher return, it is accompanied by a higher risk, right? The standard deviation is a little bit bigger. And you usually see that, you can see that pattern. And that's showing you the risk return trade-off, right? So you're going to get a higher return, but it's probably going to be matched with higher risk. And if you took the time and reviewed the discussion in the risk and return lecture notes, I talk about that looking at different asset classes over time. To compensate investors for taking the additional risk, they would expect a higher return. And that's why that works out that way. It's like a self-fulfilling prophecy. Okay, so now what I want to do is not think about them. Well, actually, I want to decide which one should I hold. So there's a trade-off here. And so if I ask you, which one would you buy, A or B, if you had the money, you had the capital to buy it, which one would you buy? The answer is it depends. It depends what kind of investor you are. If you're risk averse, and most people are, when you're presented with two securities with comparable returns, you'll choose the one with the lower risk. So in that case, if you're risk averse, you'd go with A. So the way you look at that again is with 6% plus or minus. You guys, hold on. I have somebody here. Give me a minute. Okay, sorry. I have a technician coming. Feel bad. I'm gonna have to interrupt if he ever shows up. Okay, so this is 19.6%. So we would look at this as the mean plus or minus, right? Mean plus or minus the standard deviation. And you think within one standard deviation, we're already in the negatives. And this one with 7%, it's like just terrible, right? 22%, we're way in the negatives with just one standard deviations from the mean. And the chances is a 68% chance of that happening if we believe they follow normal distribution. But even if we don't believe it follows a normal distribution, it's the case that the majority of the values will be, or more, will be within one standard deviation, according to Chebyshev's theorem, but we're not going to get into that. So it depends what kind of investor you are. If you're a risk-loving investor, presented with two securities with comparable returns, you'll choose the higher risk one. So you choose B. Now the question comes, which one are these really comparable risk? Are these comparable? Are these exactly the same? No, they're a little bit different. You could argue that's insufficient because it's still hard because these are not the same return. So another way to look at this is to combine together in a calculation what's known as the coefficient of variation, combine together the risk per dollar return or per unit return, let's say that way. So this is a measure of risk. So it's showing, it's actually exploiting the trade-off. It's putting one on top of the other, right? Remember, we did make indices or ratios before to do something looking at benefits and costs. So this is kind of like, this is the cost, the risk, but this is a return. So for each unit of benefit, the risk is 3.27 for A. And for each unit of benefit, the risk is 3.14 for B. So if you are risk averse, you want the one with lower coefficient of variation, 3.14. So that's different than what we said back here. We would have picked A, doing it this way. Just looking at the data like this. But putting them together, it looks like if we're risk averse, sorry, we're going to pick B. Yeah. Sorry, A. What am I doing? If we're risk averse investment, yeah, B, right? We're going to pick B over A. And if we're risk loving, we go for the higher one. So if you're risk averse here, you're going to pick A. So it's opposite, all right? But it's a way of combining because it's not exactly the same. This one's 7 and that one's 6%. All right, so usually you're not choosing between just two securities like this. We're more interested in in this case, because they're negatively correlated, combining them into a portfolio. So we need to learn or review the mechanics of portfolio theory, how we combine two assets. Initially, we start with two assets, but then we're going to talk about however many assets we want to combine and what are the mechanics of doing that. All right, so I'm going to introduce or reintroduce something you should have learned in statistics or in my class if you took it with me before, is combining two variables to create a new variable. And what are the mean and variance of doing that? So I'm going to create a new variable, RP. So this is the return on a portfolio of two assets. And I'm going to combine RA and RB. I'm going to spend $1,000 and I'm going to put 500 invested in A and put 500 into B. So per so what I care about is that I'm going to put 50% into A and 50% into B to get a new return. Okay, so in general, I'm going to use the notation XA and XB. Okay, so that's what XA and XB are. They're just the weights. All right, so how do we find the mean and standard deviation of this? What would the mean and standard deviation of this be? So like I say, you should have learned this in statistics. If you didn't, you could have learned it in my class. If you didn't learn it in my class, you're going to learn it now. What's the expected return of this? So if you have two, and if you don't know, again, go back to the statistics review. So if you're thinking of combining two random variables with two distributions, then what is there? And we're going to add them in this way. We're going to take a fraction of A's return and a fraction of B's return and put them together. What's going to be, how is that going to change the expected return? So I'm going to grab this information here. So it turns out that like this is another average, right? This is a weighted average. If I use 50% and 50%, this is just like a regular average because it's even, but it doesn't have to be 50-50. So this is a weighted average of returns. So the rule is the mean of the average of two variables is equal to the average of their means. Okay, so that means this is the average of two variables, right? And now I want to get the average or the mean of the average of two variables. But this is just going to be the average of the two means. So how that works is you imagine E, we call E an operator. It's a linear operator. And the XA and XB are just numbers. They don't have an expected value. I mean, they're just themselves. So if I work this operator through this whole expression here, then this is just going to be the same thing, but rather than the average of the R's, it's the average of the means. So look at that. Think about that for a minute. So you see the pattern. So I'm just replacing RA with the mean of RA. So that's convenient. So basically, if I take two variables and I average them, their mean will just be the average of the two means. That's what it's saying. So in terms of returns, if you're investing and getting 6% for A or investing and getting 7% for B, if you invest in both equally, then you're going to get 6.5%, the average, which makes sense. Okay, so if you do calculate this, that's what you're going to get. This is going to be 0.5 times 0.06 plus 0.5 times 0.07, and you get 6.5%. So that's the solution of what is the averages of this new variable you created. But now the question becomes, what is the variance? Now, would the variance have the same property? So this is my question for you. Would the variance also be the same? So remember, I have to work with variance and then take the square root, right? Is that how I do it?
Is the V supposed to be the variance?
So this other one was the um, expectations operator, and this is V for variance operator, yeah.
Wouldn't the numbers then be different?
What do you mean?
I mean, if you're not, okay, so R keeps being R, doesn't matter if it has an E or a V.
Well, I'm not saying this is the answer. I'm saying, what would it be? Would this possibly be the answer? So over here, let me move it over. Over here. So is it just that easy? Do I just do that? And if I don't, why? And like, what's the difference?
I don't think you would do that because they're square roots.
or squared, right? So to
Yeah.
get the
They're
variance, we
squared.
squared all the values, and we usually use a standard deviation, so this should feel uncomfortable. So what if I make it, so this is not it. What if I made it, is that better? And I'm going to show you where that comes from in a minute too. If the technician doesn't show up right away. So this is only true, this is true only if um, A and B are not correlated. In other words, covariance of RA, RB, or we write like sigma AB is equal to 0. Okay, so if there's no relationship between them, then the variance of a portfolio holding both of them is just their components, just their contribution, each of them. And we have to square because I will show you later why, but I can write this as sigma A squared. And okay, so that is true as long as the combination of having A and B doesn't, there's no relationship between them. If there's a relationship between them and that has an effect, we need to include it. But there's, if we assume there's no relationship or we know there's no relationship, it's just these two contributions to the variance. But what did we know? What did we see? Is there a relationship between them? What did you guys tell me about this data? Is there a relationship? What kind of relationship is it?
I think Aidan said it. It's inverse the between negative and positive.
Exactly, negatively correlated,
It
right?
was actually Hector.
Oh, was
But
it
yeah,
Hector? Oh, then. Okay, you guys sound the same. Okay, so that's so honest of you. Um, okay, so they are related. It's not positively, but negatively correlated, still related. So then this can't be the answer. So we have to have an extra term. So let's talk about that. This is the extra term here. And we're going to review where that comes from. But for now, what I want you to do, and you had the painful test I gave you last on Monday, to practice calculating the covariance. So using this data here, and I have to get the original distribution. Calculate the, oh, I have to get rid of this. Calculate the covariance. So the covariance, so basically right now, so this was what we talked about. This makes sense. But because there's a relationship between A and B, we want to capture that as the total part of the total variance. We have this extra term that I'm going to justify momentarily, but right now I just want you to get the covariance term. So this is the crazy looking formula, but you know it's just a matter of two sets of two brackets and the probability in front and the means here. So this one is for A, so it's 0.06. And this one's for B, 0.07. And then you put the information for A here, 0.3 minus, oops, and negative 0.1 minus. I already have the minuses in there. And then here for B, negative 0.2 minus and 0.25 minus. Okay, so you're going to multiply those across, store 1 and store 2, and add them up. What do you get? Anybody got an answer?
Should it be negative?
Yes, right? Exactly, because they're negatively correlated. You should get a negative. Very good. Oh, he's here. Okay, you guys keep working on that. I'll be right back. you miss me? I'm back. All right. So what'd you get?
Hey, don't put it in the chat. It's negative 0.0432.
Like this?
32 at the end. You put 38.
44848. 48 what?
No, it's a negative 0.0432.
0432. Okay, good. You all got it. All right. So that is the covariance. Now we're going to put it in here and calculate the variance. Then you take the square root. So you guys are going to check that, and using the variance as opposed to the square root of the variance is better. So I use this, like I use the whole variance number, because when you take the square root, you have to round, and rounding gives you different answers than what I want to demonstrate. So anyway, I put all the numbers in here and I get this. Look at this small number. Taking the square root is this, reminding you what A and B were initially. Let's go back and copy this one more time. So A and B had, oh, sorry, and I have to get, I didn't want to get that. I wanted to get this. Sorry. So initially we have A and B with standard deviations of 20 or more. But if we have both A and B in our portfolio, the standard deviation goes down to 1.22. This is an example of diversification. Why does this happen? So if we have a portfolio of two assets, we're going to have an average of 6.5 and now a standard deviation that even within 3 standard deviations of the mean, is still going to be a positive return. It's like, that's a guaranteed income there. You're going to be making money. You don't have to worry about it. Like almost 100% of the time, you're going to get positive return on your money. Okay? So why does it happen?
It,
Because the two assets have a negative covariance.
That's right. So when one does poorly, the other one has hedged. This is an example of hedging. You've hedged the risk. So when this one does poorly, when B does poorly, A does well, and even better. Right? It's more. It's like you're left with a net, better off here. And then this one, if you end up in this state of the world and A does poorly, then B compensates. So it works out that when all is said and done, your risk measure is 1.22%. So this is an
Professor,
example of diversification. Yeah.
I have a question because when I was doing it, I got it wrong. I mean, not really wrong, but just different a little bit of a different number because it says there that that 0.22 to the power of 2 is 0.0486, but it's 0.0484 in my case. Like when I did it, like when I do You know how, like, is that the standard deviation of B? Right, yeah. It's to the
Listen, this
power of,
one is just the variant. I put the variance inside.
okay, so yeah, on the other one. Yeah, on that one, the variance of V, no. Instead of 0.086, it got me 0.084 on the, no, on the second one.
Second one where? Sorry, where are you?
Where it says 0.0086.
0.086. Where's
Yeah.
0.086?
Next, okay. I don't know how to explain. I'm sorry. At the,
Point
yeah,
zero four eight six.
yeah. Instead of that, it gave me 0.084.
But that
I
is
don't know.
that's for the standard deviation. That's a variance. Sorry, that's over here.
That's fine.
We never calculated them. They were just given
Okay. Okay, that's fine.
because we did them before. They were done back here. And I told you to verify them here. See?
Oh, okay. Thank you.
That's where they're from. Okay. Are you on track?
Yes.
So this is an example of diversification, and it looks like well, the covariance being negative reflects diversification. Okay. So it's that term, it's that covariance term that's going to reduce your risk. Okay, so we have some time still. So now we did this for two securities. Before we go on to the next material where I discuss implications, so this funky looking formula is going to reflect what we're going to do next. We're going to do this for 3 assets. What would be the formula for 3 assets? If this is the formula for variance of 2 assets being combined, what is the formula for 3 assets? So the issue is, where does this come from? This formula comes from considering the relative contributions of the fraction of security A invested, fraction of security B's return, and taking them in turn, in pairs. We take them in pairs. And we think of them, each pair and their covariance. Okay, so what is this? How can I simplify that? So let's look at this. The easiest way I find to explain this is using the formula for covariance, like this one here. I'm going to adapt this formula for the historical returns data, right? I'm going to adapt it to do it for this. So covariance XA RA XA RA is equal to, so I'm going to I'm going to put it underneath here. So what does it look like? It's going to be 1 over n minus 1. So the first one is x. So it's going to be xa. So x here is a variable, but x here is a weight. Okay, so it's xa is the weight. Ra minus xa. Ra, sorry, let's do that again. So you have to do the mean of XARA. And this one is XARA as well, minus the mean of XARA. All right, so how do I simplify this? What can I do to make it look like something more familiar? I can factor out the scalar XA. Are you guys awake? You're paying attention?
Can't you also factor out RA?
No, because this, remember that E of XARA can become XARA. They get separated, right? Because I showed you that before, that this can come out because it's just a scalar. So the mean of an average, remember that whole discussion, is equal to the average of the means. It's the same thing here. So this becomes, oh, I'll do this. I'll change it over here. So these get separated like that, and this one too. And so what I can write is, you guys should just be watching. If you're trying to write, like there's no point because it's in the notes and everything. I mean, it's in the videos. You guys can look at that later. Just watch me do this. So if I remove XA from both parts, this leaves me RA minus ERA. And the same thing happens here. How can I group my terms? And what do I get? And what is that?
Isn't that similar to the variance?
It is the variance. Very good. So there you go. What is this? How do I simplify this then? It is actually the first term in my formula. It's XA squared sigma A squared, which is the variance. So that's where that first term comes from. That's that. So you see where the squared comes from because you have to square. Square comes from is because you have to do this twice. So that's where you get an XA out of here and an XA out of there. The deviation from the mean square, that whole concept squares your weight in front, any fraction that you're going to put in front. Okay, questions about that? So given that we got this one, what's this one going to be?
Same thing, but would it be instead of an A?
Exactly. You guys remember this from before or no? That's going to
Yeah.
be that one.
You call it the matrix, I think.
This is the matrix, yeah, the matrix method. Okay. And now what are these going to be? Do we need to do the long way? We can do the long way to show ourselves. But let's do that. Let's do it the long way. So the long way is that we're going to write it out. Covariance XARA XBRB is equal to 1 over n minus 1 XARA minus XAERA, and then this one. And you guys never have to write this again if you understand. I'm just writing all this out to show you what's behind what you're doing. You don't have to. I'm not going to test you on proving it. The point is this is supposed to help you understand and remember the formula better because you know where it comes from. And adapt it for the case of more assets. That's what the point of this is. So now what happens? How do we FOIL out? How do we not FOIL out, but factor out? What do we factor out of each of them? Let's factor out XA, and that one factor out XB. And what does it leave?
RA and ERA?
RB and RB minus ERB. So this is what? This is XA, XB, covariance AB. And I hate when it does that, when it changes the font size. All right. Okay, so it's because I'm zooming in and zooming out. It does that to me. So this is equal to XA, XB, covariance AB. All right, so this one is going to be the rest. This one here. I have one of those. But there's a second one. Where's the other one? So adding these contributions of volatility or variance together gives you the formula for variance of RP, the newly or the portfolio, the newly created asset of two assets. This is the other one. Why? Well, if I put this out into a formula, basically this one would come first. I would just reverse these. But it's the same thing, right? I would just put B first and A over here. Would that change the result? Well, you could say I would get XB, XA, and sigma BA, but isn't it the same thing? Does it really matter if I put this bracket first or the other bracket first? No. Okay, when you're multiplying, it's added, it's what's the word? Associative property. You can move them around. So this is the same as this. I have another one. Oops. I have to erase that first. It won't work. It's all about the covariance. That's why I tortured you with the covariance calculations the other day. To get you aware, like this is at the heart of everything. So we're considering their coincidence, their covariance. We add up all the components together and we get this. That's where the formula comes from. So for next class, for next week, other than just studying overall everything, for CAPM and like there's several exercises in the CAPM material. You can get started with the statistics calculations and work ahead because you have 5 days. Wednesday, Thursday, Friday, Saturday, Sunday. You have 5 days before I see you. What is the formula for 3 assets? What is the formula for mean and standard deviation? Not to mention, that's the variance, right? We have to take the square root of that in the end, but that's besides the point. So what's the mean? What about the mean and standard deviation for this variable, XA RA plus XB RB plus XC RC? Another stock. How would it change the formulas? So you guys can go. You have another class, or you're going to take a break, or you're going to go home, wherever you are. But next week, that's where we're going to start, and we're going to finish these notes and hopefully get into the last set of notes. I need to spend some time with you on Markowitz portfolio theory, so please read ahead and watch videos ahead in anticipation of that. Try and finish CAPM before Monday if you can, the second set of notes and exercises, and bring me your questions. Alrighty?
Cool.
Very cool. All right, so have a good weekend. You guys are going to keep me posted. Isabella was very quiet today. It's all easy for you, right? You remember all this stuff.
Yeah, I already even have. I still have the 3 asset formula
Okay,
that
good.
we did.
On your formula sheet, good, good. So you're going to share that with your compañeros there. Okay, guys, have a good weekend and keep me posted if there's anything. I have another class now. If you need to meet with me or ask me anything, you can text and we can make arrangements, okay? Even though I'm leaving tomorrow, I'm available to you. Class goes on. Bye.
Thank
Are
you
we
for
in the same
that,
place for next
Professor.
class?
Whoa. One at a time. Derlim, what?
Are we in the same link for next class?
Yeah, it's always the same link. Yeah.
Okay. I'll wait.
Yes. Dosan, you're okay?
Yeah, see you next class, Professor.
See you then. Bye.